Welcome to Bhagaskara Labs. In this session, we're going to learn about one of the most important concepts in AWS networking, VPC Peering. VPC Peering allows us to connect two different virtual private clouds so that instances inside them can communicate securely using private IP addresses without relying on the public internet. In this tutorial, we'll take a hands-on journey, step by step, from creating VPCs and subnets, building VPC endpoints, launching EC2 instances, and testing connectivity, all the way to establishing a peering connection and verifying successful communication. By the end of this video, you'll understand not just how to configure VPC peering, but also why it's such a powerful tool for building scalable, secure, multi-VPC architectures in AWS. VPC peering is essentially a private networking bridge between two virtual private clouds in AWS. Think of it as creating a direct road that allows traffic to flow between two otherwise isolated neighborhoods. First, this connection lets resources in one VPC communicate directly with resources in another using private IP addresses. There's no need for public IPs, so communication stays inside AWS's secure backbone network. Second, unlike VPNs or internet gateways, VPC peering doesn't rely on the public internet. This reduces exposure to external threats, while also simplifying setup, since no extra hardware or third-party tunnels are needed. Third, a VPC peering connection is always one-to-one. If VPC A is peered with VPC B, and VPC B is peered with VPC C, A cannot automatically talk to C. Each relationship must be explicitly defined. Fourth, the performance is excellent because the traffic never leaves AWS's internal infrastructure. That means you get low latency and high throughput at a cost lower than traditional networking solutions. And finally, VPC peering is versatile. It works within the same AWS account or even across different accounts and regions, making it a powerful tool for multi-VPC and multi-environment architectures.
So why should we use VPC peering in the first place? First, it provides secure private communication. All traffic between VPCs stays inside AWS's private backbone network, never touching the public internet. This reduces the attack surface and ensures a higher level of security. Second, VPC peering gives us low latency and high performance. Since the data doesn't go through external networks or complex tunnels, communication between VPCs is fast and reliable, perfect for real-time applications. Third, it's cost-effective. Unlike VPN or Direct Connect, there's no additional hardware, no physical connection, and no third-party costs. You simply pay for the data transfer at AWS's standard rates. Fourth, VPC peering supports cross-account and cross-region connections. That means we can connect environments owned by different teams or even link VPCs across AWS regions to build global applications. And finally, it helps simplify architecture. With peering, we can share resources like databases, application servers, or VPC endpoints across multiple VPCs, avoiding duplication and making our infrastructure easier to manage.
Here is the workflow we'll follow in this lab. First, we create two virtual private clouds, each with its own CIDR range, subnet, and route table. Second, we add a VPC endpoint to each VPC. This endpoint allows us to connect to our EC2 instances securely and privately from the AWS console without relying on public IPs. Third, we launch one EC2 instance in each VPC. These instances will serve as our test machines. Fourth, we test connectivity before peering. At this stage, the two instances cannot communicate with each other because the VPCs are still isolated. Fifth, we establish a VPC peering connection. We create and accept the peering request, and then update the route tables to allow cross-VPC communication. And finally, we test connectivity after peering. This time, the two EC2 instances should be able to reach each other privately through the peering link. This is the end-to-end workflow we'll demonstrate step by step in the hands-on session.
We begin our workflow by creating two separate virtual private clouds, which we'll call VPC-A and VPC-B. Each VPC needs its own CIDR block, which defines the IP address range for that network. For example, VPC-A might use 10.0.0.0/16, while VPC-B uses 192.168.0.0/16. Inside each VPC, we create subnets, smaller network segments where we'll later launch our EC2 instances. Subnets help us organize resources and control availability zones. Next, we configure route tables. A route table defines how traffic flows inside the VPC and whether it can reach outside networks. At this stage, the two VPCs remain fully isolated, meaning no communication is possible between them. By finishing this step, we have built the foundation. Two independent VPCs, each with their own subnets and route tables, ready for further configuration.
Before we can launch and manage our EC2 instances, we need a secure way to connect to them. Normally, this would require assigning a public IP and routing traffic through the internet, which increases exposure. Instead, we use the EC2 Instance Connect endpoint. This allows us to access EC2 instances in private subnets without an internet gateway, NAT gateway, or public IP. All traffic stays inside the AWS private network, making it more secure and cost-efficient. Now, let's create an endpoint for each VPC. We go to the VPC console, choose Endpoints, and select Type EC2 Instance Connect Endpoint. Then, we specify the VPC, select the subnet where EC2 will run, and attach the right security group to allow EC2 Connect traffic. Once we create the endpoint, we wait until its status shows as available. We repeat this same process for both VPC-A and VPC-B. By the end of this step, both VPCs are equipped with private, secure access paths for managing our EC2 instances.
Now that we have VPC endpoints in place, we can launch EC2 instances inside each VPC. We will deploy one instance in VPC-A and another in VPC-B. These two instances will serve as test machines to verify connectivity before and after peering. For security groups, we configure them carefully. Each instance allows SSH access from its own VPC through the EC2 Instance Connect endpoint and ICMP traffic from the other VPC to enable ping testing. At this point, the instances remain isolated. They can be managed through their VPC endpoints, but cannot yet communicate across VPCs. That communication will only be possible once we establish VPC Peering later.
With both EC2 instances running, we now test connectivity between them before VPC peering is established. We use the EC2 instance connect endpoint to securely access each instance. From the EC2 instance in VPC A, we try to ping the private IP of the EC2 in VPC B. As expected, the ping fails because there is no route between the two VPCs. Next, we switch to the EC2 in VPC B and ping the private IP of the EC2 in VPC A. This also fails for the same reason. The two VPCs are fully isolated by default. These failed tests confirm the baseline. Without VPC peering, EC2 instances in separate VPCs cannot communicate with each other.
Now it's time to connect the two networks. We do this by creating a VPC peering connection between VPC A and VPC B. First, we create the peering request from VPC A, selecting VPC B as the peer. Then, in VPC B, we accept the request. At this point, the peering link is established, but traffic still won't flow until we update the route tables. Next, we edit the route table in VPC A and add a route pointing to the CIDR block of VPC B, with the target set to the peering connection. We repeat this process in VPC B, adding a route to VPC A's CIDR block through the same peering link. With both route tables updated, the two VPCs now have a direct private connection and can communicate securely over the AWS backbone network.
Now that the VPC peering connection is established and the route tables are updated, we go back to the EC2 console where we previously accessed our instances. From the EC2 in VPC A, we ping the private IP of the EC2 in VPC B. This time, the ping is successful. Next, we switch to the EC2 in VPC B and ping the private IP of the EC2 in VPC A. This also succeeds. These successful ping tests confirm that the two previously isolated VPCs can now communicate privately and securely over the AWS network. And that wraps up our complete hands-on lab on VPC peering in AWS. Today, we created two fully isolated VPCs, launched EC2 instances in private subnets, and configured VPC endpoints for secure access. We tested connectivity before peering and saw firsthand that the VPCs couldn't communicate initially, which highlights the default network isolation in AWS. Then, we established a VPC peering connection and updated route tables. After that, our EC2 instances could communicate privately and securely across VPCs without exposing them to the public internet. This demonstrates how VPC peering provides a safe, reliable, and cost-efficient way to connect resources across different networks while maintaining full control over traffic flow. By following these steps, you now understand not just how to configure VPC peering, but also why it's an important part of building secure cloud architectures. If you found this tutorial useful, please like this video, leave a comment with your questions or suggestions, and subscribe to Bhagaskara Labs. Your support helps us create more detailed, hands-on tutorials on AWS and cloud networking. Thank you for watching, stay curious, and we'll see you in the next Bhagaskara Labs video.